Okay, so today what we're going to do is we're going to talk about what are called reduced probability trees. Now remember when we looked at those, looked at the two-way tables? Sometimes we were using all of the data to get our probabilities, right? But other times we were only using one column or one row, in which case we only had to consider the probabilities that fit that particular situation. And there are two key words that you need to think about. If something, whoops, that's one too many dots. Okay. Oh, it's frozen, thank you. All right. So if something, or you might see the phrase, given that. If you see these phrases, they're restrictors. We can only think of this if that happens. Or given this, in other words, this had to happen, right? Okay? So when you see these restrictors, you know that you're dealing with with reduced probability trees, which means that we're still going to be calculating probability, but we're only going to be looking at a limited part of the probability tree to do it, okay? And that means we have to get rid of some of the information. Now that doesn't mean we're going to change the tree. It means we're going to do some slightly different mathematics in order to get there. Okay? So the first thing I want to do is look at some of those trees and some problems to show you what we're addressing. Okay. So, remember, when you saw earlier in two-way tables, sometimes you're going to have to use probability with reduced sample spaces. For example, we could only consider what the males in that one. We could only consider the ones who wanted to go to Milford Sound, that kind of thing. So that means you're not dealing with the whole sample space. And again, some of the keys for that are if you see if or given that, okay? But sometimes you just have to get that from the context. So we'll go through several of these together because I really want you to think about it. It's a little difficult. It's more difficult to visualize when you're dealing with a probability tree than if you had it as a two-way table. So I don't know why they didn't just give you these as two-way tables, but clearly you're going to have to read both, so that's why we're working with it. So here we go. So we have is a new formula, and it's the formula for a reduced sample space. If you have to reduce the sample space, then we're going to have to take out some of the information, right, from the tree, because the probability tree gives you all the possible outcomes. And we're going to do that by simply saying the reduced sample space probability is the probability of both events occurring divided by the probability of the given event occurring. And go ahead and write out at least both events occurring divided by given event occurring. Write out the formula there for me so that you can come back to it. And we're going to explain what that means and look at several examples. It's really quite simple once you get the grasp of it, right? Simply means we're going to be using only part of it, because most people would think that you could just read the right tree branch and be fine, but it's not really what's happening. Yes.
When it says both things are common, does it mean all potential outcomes?
Well, yeah, it means both of them happening at the same time, right? So probability of, like we're going to look at one where they're playing a game, probability of it being a home game and they win. Those two probabilities, both happening, right? Because it could be a home game and they could what? Lose, right? Okay, so we're going to have different probabilities. All right, so everybody got the formula. So let's look at an example here and talk a little bit about why we're doing what we're doing. It says, look at an example involving a team winning or losing depending on whether they play at home or away. Depending on what? They're playing home or away. So in other words, they're limiting us. They're giving us some restriction here. Okay? So let's say we're looking at their wins. Just out of the blue, I'm just saying, we're going to look at their wins, right? How many branches end with win? 2, right? But one of those branches is away and the other one is at home. Okay? And we're not allowed to consider the entire tree. So we're not going to consider those parts. Well, if I just drop those off, look what's happening. Now, do these add up to 1s? Would these 2 probabilities add up to 1? No. So what we've done is we've restricted the parts we can look at. We're only allowed to look at wins. Okay? So we have to compensate for that by getting rid of some other information. Okay? So do you see why we have to use a different formula? Because we're literally taking parts of the tree away. So it won't work just by reading the branch. Because if you wanted to know home and win without any restriction, we'd just read home, then win, right? But this one says home or win depending on where they played. So we're only looking for, it just says winning or losing. So it just says we just want all the wins. So we're only using the win column. So if this was a two-way table, right, they would either win or lose. They would either be at home or away, right? And then you'd have the totals there. And if we're talking about wins, we'd be talking about this column, right? So to me, this would be a lot easier with a two-way table. But they're going to show it to you with a probability tree. And doing that means that you're going to have to get rid of some stuff that you don't want. Everybody see why it's different? Okay, because we have a reduced probability. All right, so there's our tree. Let me just get rid of all the junk I wrote on it. All right, so there's the tree showing all the probabilities. Nothing's missing, right? So we don't have to worry about that. Let's look at our question. Using the probability tree, we can find the probability of the team played at home given that they win a match. Okay? So what is the word there that is my restrictor? Given that they win a match. So that tells me that all I'm concerned with are their wins. And from that, I'm going to select the number of wins or the probability that they won playing at home. And again, it looks like you can just say, okay, well, that's home and win, right? But it's not. Given that they won means that I'm not allowed to consider any place where they lost. So that's reducing the amount of probability, or changing the amount of probability. Is it making sense? Okay? It's really not very complicated, but sometimes it's a little harder to grasp. Okay? So what I need to do then is I need to use our new formula to solve it. So the first thing, you can read from the table the probability of both events occurring, playing home and winning. So just looking at your tree, playing at home, I'm not drawing, am I? Playing at home and winning, what's the probability of that? Yeah, so the probability of being at home and winning is 0.48, right? And again, if we were just considering every possibility, that would be our probability, yeah? But we're not allowed to consider their losses. We're only allowed to consider their wins. So I now have something else that I need to do to be able to finish the problem. So we read straight from the table, we read that probability. Yeah? No big deal. We can then calculate the probability of the given event occurring. In this case, that's any winning. Okay? Because we're looking at winning. So any winning. So what the probability of winning, there are two of those. You can either win at home or you can what? Win away. Okay? All right? And notice that it's home or away, so you get what between them? Plus. The or rule, right? So you're either going to win at home or you're going to win away. And that's just the probability of every win. Okay? All right. Well, the probability of win at home, we already know, is 0.48, right? If you follow the tree, if you look at the tree, probability of winning away is 0.22. And we're simply going to add those together, which gives us 0.7. Okay? So that's every probability, right? The probability that you won. You okay with that? Now what we have is our two probabilities. And here's what they meant by both. Here is the probability of both happening, right? So probability of both happening is which part of the new formula? It's the numerator, the top number, right? And here is just the probability of winning, period, no matter what. Do you agree? So what we're going to do is simply take that divided by that. Okay? We're going to divide out the probability of win from the probability of home and win. And when you do that, round it to 3 decimal places. Raise that last one a little bit. That's going to drive us crazy. When you do that, you end up with 0.686, rounded to 3 decimal places. Okay? So not difficult, but you need to know, thank you, but you need to know, first of all, when you have to do it, and then you have to know the calculations for it. Okay? So look okay? Yeah, nobody likes this one. Everybody's thinking, two-way table. Come on, why are we doing it this way? Yeah? But some probability trees can get bigger and just makes it a little easier. So there we go. So there's our first example. So let's look at another example. And I want you to help me work through it. Okay? All right. So this one. Another one to solve reduced sample space problems. And again, they're not going to tell you this is a reduced sample space problem. You have to look for the keywords or phrases to tell you. On an average night, a takeaway store takes 32% of customer orders for fish and chips and 68% of orders for hamburgers. Of the hamburgers that ordered fish and chips, 64 request tomato sauce. Of those customers that order hamburgers, 87% request tomato sauce or tomato sauce. Ketchup. Okay, so, all right? So that gives you the information to draw your tree. You've got either fish and chips and burger, right? That's the first set of branches. And the second set of branches is going to be what? Yeah, with sauce or no sauce. Okay? Off of both of those. Everybody okay with just making a basic tree? All right. So, if a customer requested sauce, so there's your key phrase. So you see the word if. So in other words, we're only allowed to consider the ones where the customer did what? Requested sauce. Okay? If the customer requested sauce, so that's your key phrase, what's the probability that they purchased a hamburger? Okay? So that word if is restrictive. And we have to consider that as we go. So first, create the tree diagram. Now, they didn't give you all the probabilities for everything, but remember that adding the two branches of them together always has to make 100%. So from that, we can fill in the pieces that they didn't. So, for example, if they told us 32% for fish and chips, then we know 68. Well, they gave us those two, didn't they? If they tell us 36% for sauce, we could get the other one by taking 100% minus 36%, right? To give you the 64%. So if you're missing pieces, always remember that they have to add up. If it's decimals, they have to add up to what? 1. If it's percents, 1 is the same as 100%. Okay? So watch out if they have any missing pieces. They're easy to find. But complete the tree. Okay? Now, because of the restrictor if sauce, right? That means that I'm not allowed to use the entire probability tree. Which branches am I not going to be considering at all? Exactly, the ones with no sauce, right? Which means if I break those branches off, that means I can't just read straight across to get the information I need. I have to use that formula. Yeah? Okay. Now, excuse me. So there's our tree diagram. Everybody happy with it? And the fact that we're considering only the sauce ones is what's restricting our problem. So let's look at the solution. So to calculate the probability of customer choosing sauce, we need to know all the final probabilities. And these have been calculated below, okay? So a hamburger and sauce, right? So the probability, the probability of hamburger and sauce. So that's hamburger and sauce, right? So those two probabilities multiplied together will give us that. So that's the probability of what? Both things. So that's going to be our numerator. Okay? So I know that 59.16% is going to be my top number. Okay? All right, when I push this button, it's all going to go away, but we'll remember it, and we'll come back to it. All right, so they get the same thing we did. Okay? Then, hamburger with no sauce, they give us that one. Fish and chips with sauce, they give us that one. And fish and chips no sauce, so they've got all of those. But we're only worried about the ones that have sauce. So did you really even need the ones that had no sauce? No, I don't know why they calculated all four, because we don't care. We're only interested in the branches that had sauce, right? So if you're doing this for yourself, I see no reason to calculate those. Unless they ask you to calculate each probability for every branch, that might be different, right? But if they don't ask for it, do we need it? No. Okay? All right. The probability of choosing a hamburger given that they requested sauce is simply the probability of hamburger and sauce, right, over the probability of anything with sauce. So you can either get a hamburger with sauce or what? Fish and chips with sauce. And that's an or, which means you're going to be doing what to those two probabilities? Adding them together, right? So we get our probability for hamburger and sauce, and then in the bottom, the probability of hamburger and sauce plus the probability of fish and chips and sauce. And they just did all the math, right? Remember, you need to add in the bottom first and then divide, and that gives you 0.7428. So all you're doing is restricting some of it. All right? Does it look horrible? Okay. Now, just for fun, let's make a two-way table out of this, now that we know, since we know all the probabilities, and see if we can do the same thing with a two-way table. Because the restricted ones, they may say, we need to know both ways, because the problem may say use a probability tree. But if it doesn't say which method, does it matter which method you use? No, if they don't give you a specific method, then you don't have to use a specific method. Let's just for kicks see if that works for us. Okay, so we've got, oops, gotta make it bigger, don't I? So we've got sauce, no sauce, hamburger, fish and chips. So if we have those probabilities, yes?
What if the opposite? Because in the question I had it in percentages, should we change it to percentages?
I'm sorry?
Should we change it to percentages because in the question I had it as...
They didn't, but you could. Yeah. So you could either leave it as a decimal or you could change it to a percent. Either way, they're equivalents. And yes, you're exactly right. If you started off with percentages, technically, we usually end up with percentages. So I'm not sure how specific. We will look at some sample exams from past years, and we'll see if they're how specific they are. Okay, good question. Thank you. So you could put those percentages in there. So let's just do the sauce. The probability of a hamburger with sauce, probability of fish and chips plus sauce. Okay, so those are compound probabilities, and that's why you're doing the tree. You'd pretty much need the tree to be able to get those numbers, wouldn't you? So unless they just gave you the probabilities, you'd have to calculate them. So it's easier to use the tree, isn't it? But you could calculate them, then put them in the chart as well. And then remember that it's hamburger or fish and chips, so the total would be in addition. So hamburger with sauce was, I can't make it move without this. Then fish and chips with sauce, and then you would just add those two together and see if it gave you the same probability of 0.74. Okay? So it's the same kind of idea. All right. Okay. So this is actually in your homework. So let's see if we can do this, or let's see if you can do this. All right? So what we're going to do is we're going to work through each part of this. You're going to do it. Then we'll work it together to make sure that everybody's on the same page, right? And just so that we can know that you can do it. I need to know you can do it before we leave, okay? So I'm going to stop the recording. Okay. So first step, find the probability of both. Second, find the probability of the desired outcome, win, sauce, pass, whatever. And then just take step 1 divided by step 2 to get your final probability, your restricted probability. And that'll do it for you. Okay.